Hi, my name is Amani Smith, and this is my Lab 3 report. So, the purpose of this lab is to observe and predict the different behaviors of electrical circuits using current conservation laws. This is to expand on the idea of potential difference and conventional current. So here's a quick preview of the results. We found that the total potential difference in a DC current was negative 0.07, which is pretty much close to zero, proving the loop rule. And we found for a 10 ohm resistor, it took 11 seconds to charge, 15 seconds to discharge, and for a 20 ohm resistor, 21.5 seconds to charge and 26 to discharge. So here's a quick rundown of the key concepts. We have Kirchhoff's laws, his loop rule, which states that the total potential difference in a loop is going to sum to zero. Node rule, which means that the current going in a node is equal to the current going out of a node. Ohm's law, V equals I times R, and the capacitance formula, which states that C equals the charge over the potential difference. So here's the experiment for our DC circuit. We have two 1.5 volt batteries connected in series with an amp meter, connected to a 47 ohm resistor, connected to a 100 ohm resistor, going to a second amp meter, going back to the batteries. And a couple of assumptions were made in this setup. We define the system as being the circuit neglecting external forces, and we assume that the ammeter has negligible resistance. So to find the predicted current, we use Ohm's law combined with Kirchhoff's loops and node rules to find a current of 0.0204 amps. And we took the measurement of the actual current in our circuit and found 0.02 amps, which is pretty close. And when we replace the ammeter with the voltmeter, due to the voltmeter's high resistance, the ammeter will read zero. And the voltmeter we measured was 2.7 volts or in the circuit. And this is pretty close to the 3 volts which two batteries supply. Here we have the potential drops for the 47 ohm resistor, negative 0.09, and then for the 100 ohm resistor, we have negative 1.87 volts, and we can see for the 47 ohm resistor it's less steep than the 100 ohm resistor, since this causes a greater potential difference. Here we have the potential sum. The sum of the potentials 2.7 from the battery, and then subtracted by the two potential differences from the resistors gave us a total potential difference of negative 0.07 volt. In actuality, it's supposed to drop to zero. However, negative 0.07 is a good approximation. When we attach a voltmeter, due to its high resistance, there is negligible current going through. This is why the reading for the ammeter remains constant. So next we paired that ammeter in parallel with a 100 ohm resistor, and we recorded a current flow of approximately 0.04 amps. And due to the ammeter's low resistance, this causes more current to flow through it. This current otherwise without the ammeter would be going through the resistor, decreasing the current. Here we're going to use Ohm's law to find the resistance for each resistor. For the first resistor, just gave us 45 ohms, which is a pretty close approximation to the 47 ohm resistor value which we were supposed to get. For the second resistor, we have 93.5 ohms, which is pretty close to 100 ohms. Here we assume that both the wires and the ammeter has negligible resistance, so it's going to have a potential difference of zero. So here for our RC circuit, our setup was two 1.5 volt batteries, a 1 farad capacitor, and we placed these in series with first a 10 ohm light bulb and then a 20 ohm light bulb. And these are the times it took for the capacitor to charge and discharge. So now for the potential round trip, we found discharging time of 28.5 seconds. However, in actuality, we had a discharging time of 11 seconds. And some potential sources of error could be due to rounding assumptions made. We also neglected external forces, and there could be measurement errors. So now for our discussion questions. What if you charge a capacitor with no resistor? Well, in an ideal circuit with no resistance, the capacitor would charge almost instantaneously. To have zero resistance is almost impossible because even wires with negligible resistance still have some sort of resistance going through, causing the current to slow down. And when we took our measurement of the circuit charging the capacitor with no resistor at all, we had a charging time of 7.5 seconds, which is clearly different than the ideal model of zero.